5.13. A short bar magnet placed in a horizontal plane has its axis aligned along the magnetic north-south direction. Null points are found on the axis of the magnet at 14 centimeter from the center of the magnet. The Earth's magnetic field at the place is 0.36 Gauss and the angle of dip is 0. What is the total magnetic field on the normal bisector of the magnet at the same distance as the null point? It implies at 14 centimeter from the center of the magnet. At null point, field due to the magnet is equal and opposite to the horizontal component of Earth's magnetic field. Now, say, short bar magnet is placed in a horizontal plane. Axis aligned along the magnetic north-south direction. Okay, so this one is north pole of the external magnetic field. This one is the south pole of external magnetic field. And null point is found on the axis of the magnet. So if the magnet is placed in such a way the north pole of the magnet is towards the north and south pole of the magnet is towards the south of external field, then the magnetic field of your magnet on its axis that will be in the direction of its dipole moment south to north. So in this particular direction, right, which one is represented here by this blue arrow. An external field that is in the opposite direction, then and then only you will get the null point on the axis of the bar magnet. Clear this concept? Here, if the north pole of the magnet is towards the north of external field and south of the magnet is towards the south of the external magnetic field, then and then only the null point will be on the axis. And on equatorial line, you will never get the null point. But if the magnet is in the opposite direction than shown in this figure, then null point will be obtained only on the equatorial line. You will never get the null point on the axis of the magnet. Now see, the distance that is given to you for the point R, that is 14 centimeter, so 0.14 meter. The horizontal magnetic field of Earth, that is 0.36 Gauss, that is 0.36 into 10 raised to minus 4 Tesla. Now, you are getting null point at 14 centimeter on the axis. It implies that the magnetic field on the axis at that point, that is exactly equal to Earth's magnetic field magnitude-wise, and both are opposite that we discussed in the figure. So we can write Bx is equal to mu 0 upon 4 pi 2m upon r cube, that is on axis. Now He 0.36 into 10 raised to minus 4, that is equal to mu 0 upon 4 pi, that is 10 raised to minus 7 to m upon 0.14 cube. Now solve this one, you will get m. Now at the same position, the magnetic field on the equator, so we know the total magnetic field at the same point on the equator. So at equator, B equatorial, that is B axial by 2. This one is due to magnet. B axial, that is equal to HE. Here we discussed. So B equatorial, that is HE by 2. So this is the magnetic field of bar magnet. But we want to find the total field. So total field, that is B equatorial plus Earth horizontal is already there. But here we proved B equatorial, that is HE by 2. So here if we substitute HE by 2, then resultantly we will get 3 by 2 HE. Now here substitute the value of HE, that is given to you 0.36 into 10 raised to minus 4 Tesla. Then solve it, you will get the total field. Now see here, without calculating this thing directly, you can solve the problem in this way. But why here this equation I placed? Because suppose it is asked to you not exactly at the same point, but at some other point, if you want to calculate the resultant or the total field, then in that particular case, you require M. And then you have to substitute the value of M in the equation of B equatorial. And they can ask you additionally to calculate the magnetic moment also in this case. And therefore, this portion is mentioned here. Clear to all of you?